Now that we know what conditionals are, let's talk about a few things that we can do to a conditional statement, and then afterwards evaluate whether or not we can figure out the truth of these statements after they've been changed. So let's start with a conditional P implies Q. Doesn't matter what it is. We can even think about it with the example that we just covered, being if you get A's on the next quiz, then I will throw you a pizza party. So the converse is going to be the first thing that we play with. The converse will reverse the hypothesis and conclusion in an if-then statement so that it now reads if Q, then P, or Q implies P. For example, with the pizza party example, that would be if I throw you a pizza party, then you all get A's on the next quiz. The next thing that we could do is we can do something called an inverse, and that's going to take the original if P then Q, and it's going to negate both of those, so turn them to their opposites. For instance, here we can see our not P implies not Q, and in our example it would be something like if you do not all get an A on the next quiz, then I will not throw you a pizza party. Last but not least, we have what's called the contrapositive. This one is going to negate and reverse the hypothesis and the conclusion. In other words, it does both the converse and the inverse at the same time. So I'll have not Q implying not P. And in this case, we're going to see something like if I did not throw you a pizza party, then you did not all get A's on the quiz. You can probably already tell from the pizza that the contrapositive rule will always have the same truth value as the original. Partially because it's saying if the consequence didn't happen, then surely the thing that set it off, the thing that would lead you there, couldn't have happened, as long as this is true. Because if I promise something will result from an event, then if that event doesn't happen, like if we never get that end result, it must not have had this first thing happen. It gets a little confusing to think about when we're still talking abstract, so let's see a few examples. This is the example that we're starting with. If the measure of an angle is 135, then the angle is obtuse. For each time that we change it, we're just going to check truth, because I might have told you something about contrapositive, but what about these two? Is there anything we can assume about these two? Well, let's start with the converse. The converse, remember, just flips the two parts of our conditional. So this will now read, if the angle is obtuse, then its measure is 135 degrees, which is just false. If we're thinking about counterexamples here, because remember, in order for conditional to be false, we need a counterexample, I can think of an angle that is obtuse. Let's say 140. This is going to be my counter. That is an angle that is obtuse, so my first part is true. And yet its measure is not 135, so my second part is false. I have given you a counterexample to prove that the overall statement is false. Okay, so converse, even if the first statement's true, the converse might be false. What about the inverse? Well, let's take a look at the inverse. The inverse negates the original statement. So if the measure of an angle is not 135, then that angle is not obtuse. Well, again, that's false, because I can think of an angle measure that's not 135. In fact, I can still use that 140. So my first part is true, right? That's an angle that's not 135 degrees, but 140 is an obtuse angle. So that means that the second part of my conditional is false. And again, we now have a counterexample. We know that this is false. And last, our conditional. Now we know that since this original is true, my contrapositive, not the conditional, my contrapositive will also be true. So let's go ahead and see how that works. Well, if I take this down, we can see I have flipped it and turned them to their opposites. So if an angle is not obtuse, then its measure is not 135. I mean, that has to be true, because for one, we only have a few possibilities. If angles aren't obtuse, they are going to be 90 or less than 90, right? And that means that it can't be 135, because 135 is greater than 90, so it wouldn't fit in with this first statement. Therefore, we know that this has to be a true statement, and we can see that contrapositive rule coming into play. All right, let's do one more example, because so far I'm seeing that converse and inverse, well, they're just kind of false. Is that a pattern, or is this just a coincidence? So let's say if a figure is a triangle, then it is a polygon with 3 sides. If I start with the first statement, again, I'm going to take the converse by just flipping the if and the then portion. So if a figure is a polygon with 3 sides, then it is a triangle. Well, this is actually a true statement. And we can see that quite clearly. Like, I know that when we have a polygon with 3 sides, then it's a triangle. So even though the first conditional is true, my converse is actually true as well. It's kind of nice. Let's check out the inverse. If a figure is not a triangle, then it is not a polygon with 3 sides. Well, that's just true. I mean, we've known that for a long time, right? Again, we're just checking here when I negated the first portion, the hypothesis, and negated the second portion, the hypothesis, or the conclusion, it still did result in a true statement. So not our first pattern. We know that the final statement should line up, but let's just make sure that we remember contrapositive. It's going to flip the hypothesis and the conclusion, turn them both to their opposites. So if a figure is not a polygon with 3 sides, then it is not a triangle. And once more, that's a true statement. So what we're seeing here is that inverse and converse, we just won't know whether or not these are going to be true. They might match truth of the conditional, but they might not. And so keep that in mind. These two will make like entirely new conclusions. So you can't just flip a conditional that's given to you and assume that it will work, which will be the temptation a lot. Same thing with inverse. Just because the first thing didn't happen, it doesn't mean that the result won't happen. That's actually what throws people off with our earlier example about me not giving, like, even though you guys didn't get the A, I still give a pizza party. Technically, again, it's not a lie. It could still happen that you get a pizza party, maybe for a different reason. It wasn't an A on the quiz, but you were so unbelievably competent at a certain thing, or you showed kindness and grace in a way that I just figured needed to be celebrated. We might get a pizza party anyway, or just I feel like pizza, so I threw a pizza party. There is a possibility that the result will still happen, even if the first thing doesn't. And that's something that is really easy to forget. There is one final thing that I want to talk about before we move on from conditionals. And it's a specific type of conditional. It's called a biconditional. So go ahead and flip over your paper. Let's take a look at those. A biconditional is called a biconditional because it actually has 2 conditionals in it. It is considered the conjunction, and, of the converse and the conditional, as you can see here. Basically, you can read the statement forward or backwards. So here we have P double arrow Q. In other words, this is going to be if and only if is what we have it shortened as, if and only if. And what it reads is if P then Q, you can start at P and go to Q, or if Q then P. Again, you can start at Q and move to P because it reads both ways. And that means that because I can read it 2 ways, I have 2 conditional statements, not just one. And you can already see this double arrow is read as an if and only if. A lot of times I am going to shorten this with an IFF, and you'll see that in sentences as well. Mathematicians love to shorten things. That's a shorthand that will pop up when they're writing things out with words. So biconditionals are going to be seen most often with things like definitions, because we can use them either way. We saw that when we looked at the triangle example on the front, because we found that, yes, if a figure is a polygon with 3 sides, then it is a triangle, but the reverse is true. The converse is true. If it is a triangle, then it is a polygon with 3 sides. So you see that it can go either way. So definitions will be biconditional statements that can be used in either direction. So let's go ahead and try a few of these. Like, we're going to take this and we're going to write the following as a biconditional, write the following biconditional as a conjunction of 2 conditionals. So this is where we're given the statement, coplanar lines do not intersect if and only if they are parallel. Notice here the first step is to mark what you have to work with. Look for your if and only if and block it off. Prior to that will be one of your statements. We can just say it's our P, and after that will be our other statement, the Q. And we're just going to write these as the conjunction of 2 conditionals. In other words, we're going to write 2 if-then statements and connect them with an and, because that's all a conjunction is. It connects things with an and all a conditional is an if-then statement. So let's write those two. The first one, I'm just going to read it the normal way. If P, then Q. So if coplanar lines do not intersect, then they are parallel. Now I'm going to add my second one. I'm going to use the conjunction to add my second conditional, and let's write now the converse. If two coplanar lines are parallel, then they do not intersect, and I would be all set to go. You can see I have the original conditional, if then, and its converse combined with an and. This is how biconditionals can be written, and it's also something to remember because if you're trying to prove this is true, when it's a biconditional, you actually have to prove both parts. You have to prove that this is the case, like if they don't intersect, they're parallel, and you have to prove the converse. If they are parallel, then they don't intersect. It's a lot more work, but it also means that if you've proven it, you can use it in two ways. You have two possible uses for it, which is really, really useful when you're using math in life. So you can also do that with any sort of definition, and don't forget that just because you turn something into a biconditional, it doesn't necessarily mean it's going to be true. So if they give you something like a square is a rectangle and they want you to turn it into a biconditional, find your verb, the thing that connects these objects, and split it there. You will have to make it make sense. So for instance, here, if I just said if a square then a rectangle, that means nothing, right? Like that's just a jumble of words. So turn it into a statement. Usually we're going to do this with something like a figure, if a figure is a square, or if something is a rectangle. So here's what I did for this one. A figure is a square. If and only if it is a rectangle. That is now a biconditional. And it's assumed you can read it both ways. Now, is it true? No, it's not true, because I know that I can have a rectangle, like if I have a rectangle, then it is a square. No, I can have a rectangle that is not a square. For instance, here's my counterexample. This is a rectangle. It is not a square. So this actually violates the second part of my biconditional. If a figure is a rectangle, then it is a square. Here's my counterexample. I know that this is false. So watch out for biconditionals. They're a little bit harder to prove, but they are also very useful when it comes to using definitions and using the statements that we are given. All right, that is it. Let's go ahead and practice those. Check out the work online, please.